Picture this. A single drone soars over 10,000 acres of corn in Iowa, capturing high-resolution images of every plant, analyzing soil moisture levels, detecting early signs of disease, and calculating precise fertilizer requirements, all in under 4 hours. What would have taken a team of agronomists weeks to accomplish on foot now happens in the time it takes to drink your morning coffee. This is not science fiction. This is farming in 2025, where artificial intelligence processes more agricultural data in a single day than the entire USDA collected in the year 2000. Welcome to the smart farm revolution, where century-old farming practices are being transformed by technologies that seemed impossible just a decade ago. The transformation happening across America's farmland represents the most significant agricultural revolution since the invention of the tractor. While our great-grandparents measured farm productivity by the strength of their horses and the sharpness of their plows, today's farmers are deploying fleets of autonomous machines that communicate with satellites, process real-time weather data, and make split-second decisions about crop management. The numbers tell an extraordinary story. Precision agriculture technologies are now deployed across more than 240 million acres of U.S. farmland, generating over 2.5 terabytes of data per farm annually. This isn't just about making farming more efficient. It's about fundamentally reimagining how we grow the food that feeds the world. Smart farming represents a $15.3 billion global industry that's projected to reach $28.5 billion by 2030, with the United States leading this technological charge. American farms now generate more data per acre than most tech companies produce per employee, turning every field into a sophisticated outdoor laboratory. The Midwest alone hosts over 180,000 farms equipped with GPS-guided tractors, while California's Central Valley operates more than 40,000 IoT sensors, monitoring everything from soil pH to ambient temperature. Countries like Brazil, Australia, and the Netherlands are racing to keep pace, but American agricultural innovation continues to set the global standard. This revolution matters because it addresses one of humanity's greatest challenges: feeding a global population expected to reach 9.7 billion by 2050, while using 20% less farmland due to urbanization and climate pressures. The journey toward precision agriculture begins long before any seeds touch the soil, in control rooms that look more like NASA mission control than traditional farm offices. Modern farm operations start each growing season with comprehensive soil analysis powered by artificial intelligence systems that process thousands of soil samples through spectrographic analysis. Sophisticated sensors, deployed across fields in grid patterns every 100 feet, collect baseline data on soil composition, moisture retention, nutrient levels, and pH balance. This information feeds into machine learning algorithms that create detailed topographical maps showing microscopic variations in soil quality across entire farms. Where traditional farming treated vast fields as uniform growing environments, smart farms recognize that every square meter of soil has unique characteristics requiring customized treatment. The technology infrastructure supporting these operations resembles a high-tech startup more than a traditional agricultural business. Climate-controlled server rooms house powerful computing systems that process satellite imagery, weather forecasting models, and real-time sensor data. GPS-based stations provide centimeter-level accuracy for all field operations, while high-speed internet connections ensure constant communication between field equipment and central control systems. Farmers invest heavily in redundant communication networks, often combining cellular, satellite, and radio frequency systems, to ensure their technological infrastructure remains operational even during severe weather events. The setup phase involves months of careful calibration, with technicians programming GPS boundaries for every field, establishing wireless sensor networks, and training artificial intelligence systems to recognize the unique characteristics of each farm's growing environment. As the growing season progresses, the true power of smart farming technology becomes apparent through automated monitoring and response systems that operate 24 hours a day. Autonomous drones launch from charging stations positioned strategically around the farm, following pre-programmed flight paths that cover every acre multiple times per week. These sophisticated aircraft carry multispectral cameras capable of detecting plant stress invisible to the human eye, thermal sensors that identify irrigation problems, and LiDAR systems that measure crop height with millimeter precision. The data streams directly to artificial intelligence platforms that analyze plant health, growth rates, and potential yield estimates in real time. When the AI detects anomalies, perhaps a section of corn showing early nitrogen deficiency, or an area where pest damage is beginning to emerge, it immediately alerts farm managers and can automatically dispatch ground-based robots for closer investigation. Variable rate technology represents perhaps the most impressive demonstration of precision agriculture's capabilities during the growth phase. Instead of applying fertilizers, pesticides, or water uniformly across entire fields, smart farms use GPS-guided equipment that adjusts application rates for every square meter of soil. As massive spraying equipment moves across the fields, onboard computers constantly reference detailed soil maps and real-time sensor data, increasing fertilizer application in areas with higher nutrient demand while reducing inputs where soil conditions are optimal. This precision extends to seed planting, where AI-controlled planters adjust seed spacing and depth based on soil conditions, previous yield data, and predictive models that account for expected weather patterns throughout the growing season. The result is remarkable. Farms using variable rate technology typically see from 15 to 20% increases in crop yields while reducing input costs by up to 25%. Environmental monitoring reaches unprecedented levels of sophistication through networks of IoT sensors that track microclimatic conditions across every field. Weather stations positioned throughout the farm collect data on temperature, humidity, wind speed, solar radiation, and rainfall every few minutes, feeding this information into predictive models that forecast optimal timing for planting, fertilizing, and harvesting activities. Soil moisture sensors buried at multiple depths provide continuous feedback on irrigation needs, allowing automated irrigation systems to deliver precise amounts of water exactly when and where crops need it most. Some farms deploy underground sensor networks that monitor root zone conditions, tracking how plant roots interact with soil nutrients and adjusting fertilizer applications accordingly. This level of environmental control was unimaginable just 20 years ago, when farmers relied primarily on visual observation and intuition to make critical growing decisions. The harvest preparation phase showcases smart farming's ability to optimize timing and logistics through predictive analytics that would make Wall Street traders envious. Artificial intelligence systems analyze multiple data streams, crop maturity indices from drone imagery, weather forecasting models, commodity price fluctuations, and equipment availability, to determine optimal harvest timing for every field section. Some advanced farms use machine learning algorithms that predict yield estimates down to individual plant levels, allowing farmers to allocate harvesting equipment and storage capacity with extraordinary precision. Mobile apps provide farm managers with real-time updates on crop conditions, equipment status, and market prices, enabling split-second decisions about whether to begin harvesting or wait for more favorable conditions. The technology even extends to quality prediction, with AI systems analyzing visual data to forecast crop quality grades before harvesting begins. Harvest logistics coordination demonstrates how smart farming transforms traditional agricultural operations into highly orchestrated technological symphonies. GPS tracking systems monitor the location and status of every piece of harvesting equipment in real time, while automated scheduling algorithms optimize routes to minimize fuel consumption and maximize efficiency. As combines move through the fields, onboard computers continuously measure and map crop yields, moisture content, and quality parameters, creating detailed harvest reports that inform future planting decisions. Automated grain handling systems use conveyor networks and robotic equipment to move harvested crops from field to storage facilities without human intervention, while sensors monitor grain quality throughout the transport process. Some farms deploy autonomous trucks that follow predefined routes between harvesting equipment and storage facilities, coordinating their movements through centralized traffic management systems that would impress urban transportation planners. Primary processing operations have evolved into sophisticated automated systems that handle massive volumes of harvested crops with precision that exceeds human capabilities. Modern grain elevators use computer vision systems to inspect incoming crops for quality, automatically sorting deliveries based on moisture content, protein levels, and foreign material contamination. Robotic systems handle crop cleaning and initial processing, using advanced separation technologies that remove chaff, broken kernels, and debris with remarkable accuracy. These facilities process thousands of tons of grain daily, with conveyor systems stretching for miles and automated storage systems that can locate and retrieve specific batches of grain within minutes. Quality control laboratories use spectrographic analysis and other advanced testing methods to ensure crops meet strict quality standards, with results fed back into the farm's AI systems to inform future growing decisions. Optical sorting technology represents one of the most impressive innovations in crop processing. Using high-speed cameras and artificial intelligence to inspect and sort individual kernels, fruits, or vegetables at rates exceeding 10 tons per hour. These systems can detect subtle color variations, size differences, and surface defects that indicate quality problems, automatically removing defective items from processing streams. Machine learning algorithms continuously improve sorting accuracy by analyzing millions of images and refining their ability to distinguish between acceptable and unacceptable products. Some facilities use multiple sorting passes, with increasingly sophisticated criteria applied at each stage to ensure only the highest quality products advance to final processing. The precision of these systems often exceeds human inspection capabilities while operating at speeds that would be impossible to achieve manually. Advanced processing facilities incorporate robotic systems that handle packaging, labeling, and palletizing operations with minimal human supervision. Robotic arms equipped with sophisticated sensors and AI-powered vision systems can package products in various container sizes and configurations, adjusting their movements based on product characteristics and packaging requirements. Automated labeling systems apply product information, lot numbers, and traceability codes that allow complete tracking from field to consumer. Quality control robots sample products throughout the processing chain, conducting chemical analysis and physical inspections that ensure products meet stringent safety and quality standards. These facilities often operate 24 hours a day during peak harvest seasons, processing millions of pounds of agricultural products with consistency and efficiency that surpass traditional manual operations. Distribution networks leveraging smart farming data create unprecedented transparency and efficiency in agricultural supply chains. Blockchain technology enables complete traceability, allowing retailers and consumers to track products back to specific fields and even individual plants where they were grown. Automated inventory management systems use predictive analytics to optimize storage and distribution, ensuring products reach markets at peak freshness while minimizing waste. Smart logistics platforms coordinate transportation routes and delivery schedules based on real-time data about product availability, market demand, and transportation capacity. Some distribution centers use autonomous vehicles and robotic systems to handle product loading and unloading, reducing labor costs while improving accuracy and speed. The integration of smart farming data throughout the supply chain enables more responsive and efficient distribution networks that better serve both producers and consumers. The transformation of American agriculture through smart farming technology represents more than just an upgrade in farming equipment. It's a fundamental shift toward data-driven decision-making that promises to revolutionize how we approach food production in an era of increasing global challenges. As weather patterns become more unpredictable and consumer demands for sustainable, traceable food products continue to grow, The precision and efficiency offered by smart farming technologies become not just advantageous, but essential for maintaining productive and profitable agricultural operations. The farmers pioneering these technologies today are not just improving their own operations. They're developing the tools and techniques that will feed the world tomorrow. Their willingness to embrace innovation, invest in sophisticated technology, and reimagine traditional farming practices demonstrates the remarkable adaptability and forward-thinking spirit that has always characterized American agriculture. The revolution happening in our fields today sets the stage for even more remarkable innovations in food production, where traditional concepts of farming are being completely reimagined through technologies that seemed impossible just a few years ago. If you found this exploration of smart farming fascinating, make sure to subscribe and hit that notification bell. There's so much more incredible agricultural innovation to discover together. Imagine walking into what appears to be an ordinary warehouse in Newark, New Jersey, only to discover a 12-story indoor farm producing 2 million pounds of leafy greens annually without a single grain of soil, drop of rain, or ray of natural sunlight. Welcome to Aero Farms, where lettuce grows in vertical towers stretching 30 feet toward the ceiling, bathed in precisely calibrated LED light recipes that optimize photosynthesis better than the sun itself. This is vertical farming, agriculture's boldest reinvention since humans first planted seeds 10,000 years ago. In these climate-controlled facilities, a head of lettuce travels from seed to harvest in just 16 days, compared to 30-45 days in traditional field agriculture, while using 95% less water and producing yields 390 times higher per square foot than conventional farming. The concept defies everything we thought we knew about agriculture. Crops floating in nutrient-rich mist, roots dangling in carefully oxygenated water, and harvests happening every single day of the year regardless of weather, season, or climate. These vertical farms are sprouting up in the most unlikely places: abandoned subway tunnels in London, repurposed shipping containers in Dubai, and former electronics factories in Singapore. The most ambitious projects reach heights that would make skyscraper architects proud, with some facilities planning towers exceeding 40 stories, dedicated entirely to food production. This isn't just farming moved indoors, it's agriculture reimagined from the ground up, where every variable light spectrum, humidity, air circulation, nutrient delivery is precisely controlled by computer systems that respond to plant needs in real time. Vertical farming represents a rapidly expanding $5.6 billion industry projected to reach $24 billion by 2030, with over 2,000 commercial facilities now operating worldwide. The United States leads with approximately 800 vertical farms, followed by China with 350, and Japan with 200 facilities. Singapore has made vertical farming a national priority, investing $144 million in urban agriculture initiatives to achieve 30% food self-sufficiency by 2030. The Netherlands operates some of the world's most sophisticated vertical farms, producing crops in facilities that achieve energy efficiency levels 40% better than their international competitors. These numbers matter because they represent a fundamental shift in where and how we can grow food, particularly as urbanization accelerates and arable farmland becomes increasingly scarce. Urban food production through vertical farming addresses critical challenges facing modern cities, where 68% of the global population will live by 2050. Major metropolitan areas like New York, Tokyo, and London currently import 95% of their fresh produce from rural areas located hundreds or thousands of miles away, creating supply chains vulnerable to disruption and contributing significantly to food transportation emissions. Vertical farms positioned within city limits can deliver fresh produce to consumers within hours of harvest, eliminating the need for long-distance transportation while providing year-round access to crops typically limited by seasonal growing cycles. The proximity to consumers also enables just-in-time production, where farms can adjust their growing schedules based on real-time demand from local restaurants, grocery stores, and food service operations. The startup phase of a vertical farming operation begins with facility design that maximizes growing space while optimizing energy efficiency and operational workflow. Engineers design multi-level growing systems that can accommodate anywhere from 8 to 24 growing levels within a single facility, with each level precisely engineered for optimal plant spacing, lighting coverage, and air circulation. The infrastructure installation process resembles constructing a high-tech laboratory more than a traditional farm, with specialized contractors installing hydroponic systems, LED lighting arrays, climate control equipment, and automated handling systems. Water treatment facilities process municipal water through reverse osmosis and UV sterilization to create the pure base for nutrient solutions, while backup power systems ensure continuous operation even during electrical outages. Environmental control systems undergo extensive calibration to create optimal growing conditions for each crop variety, with different zones within the facility potentially maintaining distinct environmental parameters simultaneously. HVAC systems maintain temperature ranges within 1 degree of target levels while precisely controlling humidity to prevent plant diseases and optimize transpiration rates. CO2 injection systems supplement atmospheric carbon dioxide levels to enhance photosynthesis, while air filtration systems remove potential contaminants and pathogens that could damage crops. The facility's sealed environment allows complete control over pest exposure, essentially eliminating the need for pesticides while preventing contamination from external sources. Initial testing phases can last several months as operators fine-tune environmental parameters and verify that all systems perform reliably before beginning commercial production. The growing process begins with seed germination in specialized propagation areas designed to provide optimal conditions for young plants during their most vulnerable development stages. Seeds are planted in sterile growing media such as rock wool, coconut coir, or specialized foam substrates that provide root support without soil. Germination chambers maintain precise temperature and humidity conditions while providing gentle air circulation to promote healthy root development. Young seedlings receive carefully formulated nutrient solutions designed specifically for early plant development, with concentrations and pH levels adjusted based on plant species and growth stage. Automated seeding systems can plant thousands of seeds per hour with precise spacing and depth control, while robotic transplanting systems move young plants from germination areas to their final growing positions. Hydroponic and aeroponic systems deliver nutrition to plants through carefully engineered solutions that provide all essential nutrients in precise ratios optimized for each growth stage. Nutrient formulations are mixed in computerized systems that monitor pH levels, electrical conductivity, and individual nutrient concentrations in real time, automatically adjusting compositions to maintain optimal growing conditions. Deep water culture systems suspend plant roots in oxygenated nutrient solutions, while nutrient film technique systems provide a continuous shallow flow of nutrients past plant roots. Aeroponic systems represent the most advanced approach, delivering nutrients through fine mists that allow roots to absorb nutrition while maintaining maximum oxygen exposure. These systems recirculate nutrient solutions with minimal waste, typically achieving 95% water efficiency compared to traditional agriculture. LED lighting systems provide the energy that drives photosynthesis in vertical farms, with each plant receiving precisely calculated light spectra optimized for different growth phases and crop characteristics. Modern LED arrays can be programmed to deliver specific combinations of red, blue, green, and far red light wavelengths that enhance various aspects of plant development, from stem elongation to leaf expansion to flowering triggers. Light recipes are developed through extensive research that determines optimal photon delivery rates and spectral combinations for each crop variety, with different recipes used during germination, vegetative growth, and pre-harvest phases. Energy-efficient LED systems consume 40–60% less electricity than traditional high-pressure sodium lights while generating significantly less heat, reducing cooling requirements and improving overall facility energy efficiency. Automated monitoring systems track thousands of data points throughout the facility, creating detailed records of plant development and environmental conditions that inform continuous optimization efforts. Sensors measure everything from individual plant heights and leaf color to air temperature gradients and nutrient solution pH levels, feeding this information into AI systems that detect patterns and predict optimal harvest timing. Computer vision systems analyze plant imagery to identify potential health issues, growth abnormalities, or pest problems before they become visible to human observers. Machine learning algorithms process historical growing data to identify optimization opportunities, gradually improving crop yields and reducing production costs through data-driven insights. Harvest preparation in vertical farms involves sophisticated planning systems that coordinate continuous production cycles with market demand and facility capacity constraints. Unlike traditional agriculture with distinct planting and harvest seasons, vertical farms operate on rolling harvest schedules, where different sections of the facility reach maturity on different days, enabling daily harvests year-round. Predictive analytics help farmers plan harvest timing to coincide with market demand, while inventory management systems track crop development stages to ensure consistent product availability. Pre-harvest procedures include adjusting light recipes to enhance nutritional content, flavor profiles, or visual appearance, with some crops receiving specialized lighting treatments designed to increase antioxidant levels or enhance color development in the final days before harvest. Quality control protocols during harvest preparation include comprehensive testing for nutritional content, flavor compounds, and safety parameters that ensure products meet strict quality standards. Laboratory analysis measures vitamin content, mineral levels, and antioxidant concentrations, often revealing nutritional profiles superior to field-grown crops due to optimized growing conditions and immediate post-harvest handling. Microbiological testing verifies the absence of harmful pathogens, while residue analysis confirms that products are free from pesticides and other contaminants. Some facilities conduct sensory evaluation sessions where trained panels assess flavor, texture, and visual appearance to ensure products meet consumer expectations. Harvesting operations in vertical farms demonstrate precision and efficiency that would be impossible in traditional field agriculture, with robotic systems and automated handling equipment processing crops with minimal human contact and maximum quality preservation. Robotic harvesters equipped with computer vision systems identify mature plants and perform selective harvesting that leaves younger plants to continue developing, maximizing facility productivity while ensuring optimal product quality. Automated cutting systems use precise blade positioning to harvest leafy greens at optimal locations, while gentle handling systems transport harvested products through the facility without damage or contamination. Climate-controlled harvesting environments maintain optimal temperature and humidity conditions that preserve product quality from the moment of harvest through packaging operations. Washing and preparation systems clean harvested products using ozonated water or other advanced sanitization methods that eliminate potential pathogens while preserving nutritional content and extending shelf life. Multiple wash cycles remove any growing media residue while maintaining the delicate structure of leafy greens and herbs. Centrifugal drying systems remove excess moisture without damaging plant tissues, while quality inspection systems use computer vision to identify and remove any damaged or substandard products. Some facilities incorporate specialized treatments such as UVC exposure or controlled atmosphere storage that further enhance product safety and extend shelf life beyond what's possible with conventionally grown produce. Advanced packaging systems in vertical farms create products with extended shelf life and enhanced visual appeal that command premium prices in the marketplace. Modified atmosphere packaging systems replace air with precise gas mixtures that slow respiration and maintain product freshness for extended periods, often achieving shelf lives 2-3 times longer than conventionally grown produce. Automated packaging lines handle products with minimal human contact, reducing contamination risks while maintaining consistent packaging quality and presentation. Smart packaging technologies incorporate QR codes or RFID tags that provide consumers with detailed information about growing conditions, harvest dates, and nutritional content, creating transparency that differentiates vertical farm products in competitive markets. Product finishing operations include specialized treatments that enhance nutritional content, flavor development, or visual appearance based on specific market requirements or customer preferences. Light treatments during final growing stages can increase vitamin content, enhance flavor compounds, or improve color development in leafy greens and herbs. Some facilities offer customized growing services where restaurants or retailers specify particular flavor profiles, nutritional characteristics, or visual attributes for their private label products. Hydroponic nutrient adjustments during final growth stages can influence crop characteristics such as spiciness in herbs, sweetness in leafy greens, or mineral content in specialty crops designed for health-conscious consumers. Distribution from vertical farms leverages proximity to urban markets to deliver unprecedented freshness while reducing transportation costs and environmental impact. Many facilities operate direct-to-consumer delivery services that provide same-day delivery of products harvested that morning, offering freshness levels impossible to achieve with traditional agriculture supply chains. Restaurant partnerships enable chefs to receive specialty crops harvested to order, with some facilities growing custom varieties or specific maturity levels requested by individual establishments. Retail partnerships position vertical farm products as premium offerings that command higher prices while providing consumers with guaranteed freshness, local sourcing, and pesticide-free production methods. Traceability systems in vertical farms provide complete transparency from seed to shelf, with digital records tracking every aspect of production, including growing conditions, nutrient formulations, harvest dates, and post-harvest handling procedures. Blockchain technology enables immutable records that verify product authenticity and growing methods, appealing to consumers who prioritize food safety and environmental responsibility. Some facilities offer virtual farm tours through augmented reality applications that allow consumers to see exactly where and how their food was grown, creating emotional connections between urban consumers and their food sources that strengthen brand loyalty and support premium pricing strategies. The vertical farming revolution represents agriculture's response to the challenges of feeding growing urban populations while minimizing environmental impact and maximizing resource efficiency. These soilless systems prove that exceptional crop production is possible in the most unexpected places, from city centers to Arctic research stations to space exploration missions. As vertical farming technology continues advancing and costs continue declining, these facilities are becoming increasingly viable alternatives to traditional agriculture, particularly for high-value crops grown near major population centers. The innovations emerging from vertical farms today are reshaping our understanding of what's possible in agriculture, proving that the future of farming might look nothing like its past. The success of vertical farming opens new possibilities for agricultural innovation that extend far beyond leafy greens and herbs, pointing toward food production systems that could transform entire industries and reshape global food security. Make sure to subscribe for more incredible stories about how technology is revolutionizing the way we grow, process, and distribute the food that feeds our world. Deep beneath the churning waters of the North Atlantic, massive underwater cages stretch 200 feet across and plunge 100 feet into the ocean depths, housing over 200,000 Atlantic salmon in what amounts to floating cities of fish. These offshore aquaculture operations represent the newest frontier in food production, where advanced engineering meets marine biology to create protein factories that could feed the world's growing appetite for seafood. Each cage operates like a sophisticated underwater ecosystem, monitored by autonomous underwater vehicles that patrol the perimeter, cameras that track fish behavior 24 hours a day, and sensors that measure everything from water temperature to oxygen levels with space-age precision. This is aquaculture in 2025. An industry that has quietly become the fastest-growing food production sector on Earth, now providing over 60% of all seafood consumed globally, while revolutionizing how we think about sustainable protein production. The transformation from traditional fishing to modern fish farming represents one of the most remarkable success stories in contemporary agriculture, driven by the stark reality that wild fish populations cannot sustain current consumption levels, let alone feed a world population approaching 10 billion people. While our ancestors relied on hunting wild fish with primitive tools, today's aquaculture operations use genetic selection, automated feeding systems, and environmental controls that would make NASA engineers envious. The numbers tell a compelling story. Global aquaculture production has increased by over 500% in the past 3 decades, reaching 114 million tons annually, while wild fish catches have remained essentially flat since the 1990s. This shift isn't just about quantity. Modern aquaculture produces fish with superior nutritional profiles, consistent quality, and lower environmental impact than many traditional protein sources. Aquaculture now represents a $263 billion global industry that employs over 60 million people worldwide, with production facilities operating in over 190 countries. China dominates global production with 57% of total output, followed by Indonesia, India, Vietnam, and Bangladesh. Though technological innovation increasingly comes from Norway, Chile, and Scotland. The United States operates over 2,500 aquaculture facilities, producing everything from catfish in Mississippi to salmon in Maine, while countries like Singapore and the Netherlands are pioneering land-based recirculating aquaculture systems that could revolutionize urban food production. Norway's salmon industry alone generates 11 billion annually, making it one of the country's largest export industries after oil and gas. These operations matter because they provide sustainable protein sources that require significantly less land, water, and feed than terrestrial livestock, while offering solutions to overfishing that threatens marine ecosystems worldwide. Modern aquaculture addresses critical challenges facing global food security, particularly the growing demand for high-quality protein sources that can be produced sustainably at scale. Traditional livestock production requires vast amounts of land, fresh water, and feed crops, while generating significant greenhouse gas emissions and environmental impacts. Fish farming offers remarkable efficiency advantages. Salmon convert feed to protein with 90% efficiency compared to 40% for poultry and just 10% for beef cattle. The environmental footprint is equally impressive, with aquaculture requiring 15 times less fresh water than beef production and generating 80% fewer carbon emissions per pound of protein produced. As coastal populations continue growing and wild fish stocks face increasing pressure, aquaculture provides a scalable solution that can produce premium protein sources in both marine and freshwater environments worldwide. The breeding phase of commercial aquaculture begins in sophisticated hatchery facilities that control every aspect of reproduction and early development with scientific precision that rivals pharmaceutical manufacturing. Broodstock fish, the breeding parents, are carefully selected based on genetic profiles that optimize growth rates, disease resistance, and flesh quality characteristics. These premium breeding fish live in climate-controlled facilities where photoperiod manipulation, temperature control, and specialized nutrition trigger natural spawning cycles on predetermined schedules. Advanced genetic programs use selective breeding techniques that have improved growth rates by 300% over wild fish, while enhancing disease resistance and reducing feed conversion ratios. Some facilities employ chromosome manipulation and other biotechnologies to produce sterile fish that cannot reproduce if they escape into wild populations, addressing environmental concerns while maintaining production efficiency. Egg incubation systems create optimal conditions for fertilized eggs using temperature-controlled water circulation, oxygenation systems, and automated monitoring that tracks development progress with microscopic precision. Specialized incubation trays hold millions of eggs in flowing water systems, that maintain perfect environmental conditions while removing waste products and dead eggs that could contaminate healthy embryos. Water quality management during incubation involves continuous monitoring of dissolved oxygen, ammonia levels, pH, and temperature, with automated systems making real-time adjustments to maintain optimal conditions. Hatching typically occurs in darkened environments that reduce stress on emerging fry, with gentle water circulation systems that prevent physical damage to delicate young fish during their most vulnerable development stages. Nursery operations transition newly hatched fry through critical early development phases using specialized facilities designed to maximize survival rates while promoting healthy growth and development. First feeding represents a crucial milestone, with microscopic live feeds such as rotifers and artemia carefully cultivated to provide optimal nutrition for young fish whose digestive systems are still developing. Graduated feeding programs slowly transition fry from live feeds to formulated micro-diets, with particle size and nutritional composition precisely matched to fish development stages. Water quality becomes even more critical during nursery phases, with filtration systems, UV sterilization, and biological treatment processes maintaining pristine conditions that prevent disease outbreaks that could devastate entire populations of young fish. The grow-out phase represents the longest and most technologically sophisticated period of aquaculture production, where juvenile fish develop into market-ready products through carefully orchestrated feeding, environmental management, and health monitoring programs. Modern aquaculture facilities range from land-based recirculating systems that reuse water through sophisticated treatment processes to massive offshore cages that harness ocean currents for natural water exchange. Recirculating aquaculture systems represent the cutting edge of environmental control, using biological filtration, UV sterilization, oxygenation, and temperature control to create optimal growing conditions while minimizing water usage and environmental impact. These systems can achieve production densities exceeding 200 pounds of fish per cubic meter, while maintaining water quality standards that surpass those found in many natural environments. Automated feeding systems deliver precisely formulated diets based on fish size, growth stage, water temperature, and seasonal factors that influence metabolism and feed efficiency. Underwater cameras monitor feeding behavior in real time, with artificial intelligence systems analyzing fish activity patterns to optimize feeding schedules and detect early signs of health problems. Feed formulations incorporate marine proteins, plant-based ingredients, and specialized additives that enhance growth rates, immune system function, and flesh quality characteristics. Some facilities use computer-controlled feeding systems that deliver multiple small meals throughout the day, maximizing feed utilization while minimizing waste that could impact water quality. Advanced nutritional programs can influence fish characteristics such as omega-3 fatty acid content, flesh color, and texture to meet specific market requirements. Environmental monitoring in aquaculture operations involves sophisticated sensor networks that track dozens of water quality parameters continuously, creating data streams that inform automated control systems and alert operators to potential problems before they impact fish health. Dissolved oxygen sensors, temperature probes, pH meters, and ammonia detectors provide real-time feedback on water conditions, while current meters and depth sensors monitor environmental factors in marine operations. Underwater cameras equipped with artificial intelligence analyze fish behavior patterns, swimming speeds, and feeding responses to detect stress, disease, or environmental problems that might not be apparent through water quality measurements alone. Some facilities deploy autonomous underwater vehicles that patrol cage perimeters, checking net integrity while monitoring fish health and environmental conditions throughout massive production areas. Disease prevention and health management programs incorporate vaccination protocols, biosecurity measures, and environmental controls that minimize disease risks while maintaining fish welfare standards that exceed those found in many natural environments. Veterinary oversight includes regular health assessments, pathogen monitoring, and treatment protocols that address health challenges before they impact production efficiency or fish welfare. Probiotics and immunostimulants enhance fish immune systems naturally, reducing reliance on antibiotics while improving overall health and growth performance. Water treatment systems eliminate pathogens and parasites that could threaten fish health, while quarantine protocols prevent disease introduction from external sources. Pre-harvest preparation involves careful planning that coordinates optimal harvest timing with market demand, processing capacity, and logistical requirements for delivering fresh products to consumers worldwide. Growth monitoring systems track individual fish development and predict optimal harvest timing based on size targets, market prices, and seasonal demand patterns. Feed withdrawal protocols prepare fish for harvest by clearing digestive systems while maintaining fish welfare standards, typically involving 2 to 7 days of fasting depending on species and environmental conditions. Water quality optimization during pre-harvest phases ensures fish arrive at processing facilities in optimal condition, with stress reduction measures that preserve flesh quality and minimize post-harvest deterioration. Harvesting operations demonstrate the sophistication and scale of modern aquaculture through coordinated logistics that move millions of pounds of live fish from production facilities to processing plants with minimal stress and maximum quality preservation. Specialized harvest vessels equipped with fish pumps, sorting systems, and live storage tanks collect fish from production sites using techniques designed to minimize handling stress while maintaining product quality. Underwater crowding systems gently concentrate fish within net cages, allowing efficient collection while reducing physical contact and stress that could impact flesh quality. Live transport systems maintain optimal water quality during transit to processing facilities, with oxygenation, temperature control, and water circulation systems that preserve fish condition throughout the supply chain. Stunning and slaughter procedures prioritize fish welfare while ensuring optimal product quality through methods that render fish unconscious instantly before processing begins. Modern facilities use electrical stunning, percussion stunning, or CO2 systems that eliminate stress and pain while preserving flesh quality characteristics valued by consumers in food service operations. Automated handling systems move fish through processing lines with minimal human contact, reducing contamination risks while maintaining consistent processing standards. Ice systems and refrigerated environments maintain optimal temperatures throughout processing operations, preserving freshness and extending shelf life for products destined for global markets. Primary processing operations transform whole fish into various product forms using automated equipment that maximizes yield while maintaining consistent quality standards across millions of pounds of daily production. Filleting machines equipped with computer vision systems analyze each fish individually, adjusting cutting patterns to maximize yield while maintaining uniform product specifications. Automated skinning and deboning equipment removes unwanted portions with precision that exceeds manual processing while operating at speeds that make large-scale production economically viable. Quality control systems use X-ray technology, metal detection, and visual inspection to ensure products meet strict safety and quality standards before advancing to packaging operations. Portion control systems create consistent product sizes and weights that meet retail and food service specifications, with automated cutting and weighing systems that optimize yield while minimizing waste. Value-added processing creates premium products such as smoked fish, fish burgers, and ready-to-cook meals that command higher prices while extending market reach beyond traditional seafood consumers. Byproduct utilization programs convert fish waste into valuable products including fish meal, fish oil, and collagen supplements, achieving zero-waste production goals while generating additional revenue streams. Some facilities incorporate novel processing technologies such as high-pressure processing that extends shelf life without chemical preservatives, creating premium products for health-conscious consumers. Packaging and preservation systems ensure products maintain optimal quality throughout global distribution networks that can span weeks from harvest to consumption. Modified atmosphere packaging replaces air with precise gas mixtures that slow deterioration while maintaining product appearance and nutritional content. Vacuum packaging systems remove air that could cause oxidation and off flavors, extending shelf life significantly beyond traditional packaging methods. Some premium products receive specialized packaging that incorporates time temperature indicators, allowing consumers and retailers to verify product freshness throughout the supply chain. Frozen products undergo individual quick freezing processes that preserve texture and nutritional content, while enabling global distribution to markets thousands of miles from production facilities. Traceability systems provide complete documentation from egg to plate, enabling rapid response to food safety concerns, while providing consumers with detailed information about production methods and environmental conditions. Blockchain technology creates immutable records that verify product authenticity and production practices, appealing to consumers who prioritize sustainability and responsible sourcing. DNA testing capabilities allow verification of species identity and geographic origin, preventing seafood fraud, while supporting premium pricing for certified sustainable products. Some facilities offer virtual tours and real-time monitoring data that allow consumers to see current conditions at production sites, creating transparency that builds consumer confidence and brand loyalty. Global distribution networks transport aquaculture products to markets worldwide, using specialized logistics systems that maintain cold chain integrity while optimizing transportation efficiency and cost. Air freight operations move premium fresh products to high-value markets within from 24 to 48 hours of harvest, while container shipping provides cost-effective transportation for frozen products and bulk commodities. Regional processing hubs enable value-added processing closer to consumer markets, reducing transportation costs while maintaining product quality and freshness. Some companies operate integrated supply chains that control every aspect from breeding through retail distribution, ensuring consistent quality while maximizing value capture throughout the production chain. Market diversification strategies position aquaculture products across multiple consumer segments, from premium restaurant markets that value consistent quality and availability to retail channels that prioritize value and convenience. Health and wellness marketing emphasizes the nutritional benefits of fish consumption, particularly omega-3 fatty acids, high-quality protein, and vitamins that support cardiovascular and cognitive health. Sustainability certifications from organizations such as the Aquaculture Stewardship Council provide third-party verification of responsible production practices, appealing to environmentally conscious consumers while supporting premium pricing strategies. Innovation in product development creates new market opportunities through ready-to-cook products, ethnic cuisine adaptations, and specialized products for dietary restrictions or health conditions. The aquaculture revolution demonstrates humanity's capacity to develop sustainable protein production systems that can feed growing populations while reducing pressure on wild ecosystems and minimizing environmental impact. From the precision breeding programs that create superior fish genetics to the sophisticated processing systems that deliver consistent quality products worldwide, modern fish farming represents one of agriculture's greatest success stories. These operations prove that sustainable intensification is possible when scientific innovation meets environmental stewardship, creating production systems that can provide affordable, nutritious protein sources for billions of people worldwide. As technology continues advancing and production systems become even more efficient and sustainable, aquaculture will play an increasingly important role in global food security and environmental conservation. The journey through smart farming, vertical agriculture, and aquaculture reveals how technology is fundamentally transforming food production across every sector of agriculture. These innovations represent more than efficiency improvements. They're creating entirely new possibilities for feeding the world sustainably, while preserving the environmental resources that future generations will depend upon. The farmers, engineers, and entrepreneurs pioneering these technologies today are not just improving individual operations. They're developing the tools and techniques that will define agriculture for the next century. If you enjoyed exploring these incredible innovations in food production, subscribe to join us as we continue discovering the amazing ways technology is reshaping the world around us.